Assalamualaikum and good day. We are from AS1205M and today we'll be presenting crystalline solid. But first, I'm going to talk about the objective of our presentation for today. So firstly is to understand what crystalline solids are. And next is to explain the characteristics and structural arrangement of crystalline solids. And thirdly is to differentiate crystalline solid from amorphous solids. And the last one is to explore examples, application, and relevance of crystalline solid in daily life and industry.
Crystalline solids are solids in which the particles are arranged in a very regular and repeating three-dimensional pattern known as a crystal lattice. Because of this orderly arrangement, crystalline solids have a well-defined structure. One important characteristic of crystalline solid is that they have a sharp and fixed melting point, unlike amorphous solids. This means they melt at a specific temperature. Crystalline solids are also made up of a repeating unit called a unit cell, which build out the entire crystal structure. Crystalline solid is defined as a solid material whose constituent atoms, ions, or molecules are arranged in a regular, repeating three-dimensional pattern. This repeating arrangement is called a crystal lattice. As shown in a diagram, crystalline solids have a highly ordered internal structure where particles are arranged in a fixed and predictable manners. This is different from the amorphous solids, where the particles are arranged without long-range order. Because of this ordered structure, crystalline solids usually show consistent physical properties such as definite shapes and melting points. Moving on to the key theory behind crystalline solids. First, we have the unit cell. Unit cell is the smallest repeating structure unit of a crystal. Even though it is very small, it contains all the information needed to build the entire crystal structure. When this unit cell is repeated in three dimensions without any gaps or overlap, it forms a complete crystal lattice. Next is a long-range order. This refers to the periodic and regular arrangement of particles, such as atoms or ions. This orderly pattern extends over a large distance within the solid, giving crystalline materials their definite shapes and consistent properties. Next is the type of the crystal. First is the cubic system. In this system, all three axes are equal in length and are perpendicular to each other. Because of the high symmetry, cubic crystals are very stable. Next is the tetragonal system. Here, two axes are equal in length, while the third axis is different. However, all three axes remain perpendicular. The third system is orthorhombic. All three axes are unequal in length, but they are still perpendicular to each other. This system has less symmetry than cubic and tetragonal system. Next is hexagonal. It has four axes. Three axes have the equal length in the same plane. It is separated by equal angles, and the four axes are perpendicular to that plane. Moving on to rhombohedral. All three axes are equal in length, but none of them are perpendicular. The crystal faces are identical in size and shape. After that is the monoclinic system. All axes are unequal, but only two axes are perpendicular, while the third is inclined. Finally, triclinic system is the least symmetrical. All three axes are unequal in length, and none of them are perpendicular to each other.
Next, I am going to talk about the structure, properties, and formation of crystalline solid. First is structure. Particles in crystalline solid are arranged in a fixed and repeating pattern, for example, like simple cubic, face center cubic, or even body center cubic. Secondly, is properties of crystalline structure. They are well-defined melting point and have high stability. There are also an anisotropic properties, which mean that their properties can vary in different direction and also cleavage along specific plane. These crystalline solid are also have a rigid and strong 3D arrangement. And lastly is formation. Crystalline solids are formed through slow cooling, evaporation, or solidification, which allow the particle to arrange themselves into an ordered structure. Natural processes are cooling of magma or formation of crystal like quartz, and also for industrial crystal is silicon wafer production.
Next, this slide shows examples of different types of crystalline solid. First, sodium chloride or NaCl is an ionic crystal where positive and negative ion are held together by strong electrostatic force. Next, ice and sugar are molecular crystals which are formed by molecules held together by weak intermolecular force. For iron, copper and gold are metallic crystals where metal atoms share free-moving electrons, making them good conductors of electricity. Lastly, diamond and quartz, which is silicon dioxide, are covalent network crystals. In these crystals, atoms are bonded by strong covalent bonds in continuous networks, giving them very higher strength. Next, the application of crystalline solid in daily life and industry. First, in electronics, silicon crystals are used to make semiconductors and computer chips because they can control the flow of electricity. Second, in jewelry, crystalline solids such as diamonds and gemstones are valued for their strength, beauty, and durability. Third, in the food industry, sugar crystals and salt crystals are commonly used in food processing and preservation. Lastly, in optics and photoionics, crystal like quartz and lithium niobides are used in optical lens, prisms, laser, and light modulating devices due to their special optical properties.
Now, let's move on to our case study, which is silicon in electronics. Silicon, a crystalline solid with a highly ordered crystal lattice structure. It is classified as a semiconductor because it can conduct electricity. This specific structure allows for the controlled movement of electrons. Because of this, silicon is widely used to make electronic components. You can find silicon used in many devices, including computers, smartphones, and also solar panels. Additionally, it is also known for having a high thermal stability. Now, let's take a look at the comparison between crystalline and also amorphous solid across several key aspects. First, for particle arrangement, crystalline solids have a regular, orderly, and repeating pattern, while amorphous solids have an irregular and random arrangement. Next, the structure. Crystals have a long-range order, while amorphous have short-range order. For their shape, a crystalline solids have a geometrical shape, while amorphous solids has no definite shape. Next, for the physical properties, crystalline solids are anisotropic, meaning their properties vary depending on the direction. For amorphous solids, they are isotropic, meaning they are uniform in all directions. Lastly, for the examples of crystals include salt, sugar, quartz, and also silicon. Amorphous examples are glass, rubber, plastics, and wax. Now, let's address a problem-solving question. Why do crystalline solids have a sharp melting point while amorphous solids melt over a range of temperature? The reason is that crystalline solids have an ordered repeating particle arrangement. In contrast, amorphous solids have a random particle arrangement. This difference in how their particles are organized and how they respond to heat and transition into a liquid state.
In conclusion, crystalline solids have a particle arranged in a regular and repeating crystal lattice, which give them well-defined shapes, sharp melting points, and high stability. Their ordered structure result in a unique physical properties that make them different from amorphous solid. Crystalline solids are widely used in daily life and industry, such as in electronics, jewelry, food products, and optical devices. Understanding crystalline solid is important because they play a key role in modern technology and material science.